Okay, shall we start? So, good morning, everybody. Let's start for the second part of this morning. So, my name is Sophie Bontemps. I'm working here in this lab. Most of you know me from the training organization, but I'm not only organizing training in my life, so I'm also a researcher working with remote sensing data in agriculture. And today I've been asked to talk about the classification algorithm using Sentinel-1 and Sentinel-2 data. So the presentation will be structured in this way. So some words of introduction, some reminders about the interface between the electromagnetic radiation and the land surface, and then we will jump, starting by the definition of a crop, which is probably as important as the classification in itself, and then we will go to the classification algorithm and the specificities of the Sense-to-Agri system. So, remote sensing offers a very interesting perspective of the soil because you can see it from the sky, and so there are many applications from the remote sensing data. This is not new. The first aerial photo was took at the middle of the 19th century by a French guy in a balloon, but maybe you know that the very first remote sensing image, meaning not taken by someone, was taken by a pigeon at the beginning of the 20th century, and you can see here, this is the picture that was taken by this pigeon. Well, this was very basic, but it's really opened, it was really convincing, and the technology could start. The technology went, in fact, very rapidly, with the first sensors sent in space, let's say, after the Second War, and then, you know, it as good as me, then over the 40 years, 50 years, the evolution has been dramatically rapid. Evolution in terms of spectral resolution, spatial resolution, temporal resolution. Each time you have a new sensor, you get more and more detail about your area of interest. And now we are not only talking about space sensors, but we are more and more working with sensors on board of UAV. And in the field of agriculture also, sensors on board of vehicles, platforms that will really measure your field locally, but that can provide information directly on the farmer to guide his practices. So this is evolving very rapidly. This is the overview of the sensors, where logically you know it. When you decrease the spatial resolution, you increase your temporal resolution. And in that game, the Sentinel constellation has a bit changed the game, in fact. Because with the Sentinel-1, Sentinel-2 especially, you get the decametric resolution and you get a temporal frequency, which are between the daily and the weekly one. And so for agriculture, this is what we call a game changer. So this is totally new possibilities. So the first key properties is this one, the temporal revisit. So up to 2 days using Sentinel-2 in Europe, and up to 2 days with Sentinel-1 and up to 3 days with Sentinel-2 in Europe. And this high revisit is really key if you want to monitor the agriculture dynamics. So when you want to know exactly when is your vegetation growing, if you have to monitor diseases, to detect the harvest, different kind of practices, having regular information and regular information is the key. Another key properties for agriculture is the spatial resolution. So you can see on the left the 10-meter resolution, on the right a 30-meter resolution image. So the difference between 10 and 30 is less important than between 30 and 250 between Landsat and MODIS, for sure. But in terms of what you can see on the image, this is a huge difference because then you can see the field. This is something which is new, having the field level with images that are acquired regularly and systematically. This is really what Sentinel data will allow for agriculture. So this is an example of crop type mapping when you can cover the national scale because you have the systematic acquisition, and at the same time you can go at the field level and your classification can be very very pure, very precise. And you get this information also because you get the temporal information along the season. Another example of the, let's say, field capacity of Sentinel-2, we are changing completely of context. We go to Mali. Then in Mali, a field is not what we call a field here in Europe. So a field can be some grass, some shrubs, and a very low density of plants, but still this is a field. And so the limit of your field are not as visible as it is here in Netherlands or in Belgium or in Europe. But with Sentinel-2 data, we have been able to respect the structure of the cropland area. So this resolution opens something new. And more challenging, this is to go to the crop type. So here this was an example where this was just cropland, the distinction between cropland and not cropland. But if you have the good in situ data, you can also discriminate the major crop types, even if in an environment which is rather complex, just to show the potential. So incredible opportunities with Sentinel data for the classification, but also big challenges. First one, you have to deal with the big data volume. To deal with big data volume, this is not only to buy a big cloud. This is also to optimize your processing resources, your processing algorithm, let's say, the input data that you will select. Everything should be optimal to use not too much resources. Then the decametric resolution. 10 meters is wonderful, but it also gives you a lot of thematic detail, very large variety of spectral signatures, and so this is also more difficult to get the typology, the legend, that what you want to map. At 350 meter resolution, you can say, I want cropland and cropland. Good. At 10 meter, what is your crop? What is your cropland? And then you need to start thinking correctly on what you want to map, what you can map also. And then there is this consistency issue. So over time, within and between years and over space, you have to deal with different orbits. But even with these different orbits, when you are working in national scale, you want to be consistent. And so you have to implement some magic stuff in your processing chain to deal with that. Before going to the processing in itself, I will just remind you some very basic principles. So in order to get in the end a nice information about your area, of course, you need to get very good analysis methodologies, classification methodologies. You have to get accurate data, training data set that can come either for field collection or that you can collect from existing maps or auxiliary data. Also, you have to select your Earth observation data. Do you want to work only with Sentinel-2? Do you want to add Sentinel-1? Which period will you use to map your crop? But you need also to understand your data. And I know this is an advanced training for land, but I think this is very important to remind. No, we are just letting the computer processing the data, and sometimes we just forget to think about, okay, which data shall I look at? This is not because the computer can process easily tens of terabytes of data that you need to process them. You will get a better result if you correctly understand which data or which spectral bands are important for what you want to map. And so I will be quick in the reminder, but I think this is really important that you never forget what is behind your image. This is not only binary pixel. So basically, the radiation that comes from the sun or whatever, so this is very summary of the different phenomena, but a part will be absorbed by the surface, by the atmosphere, by the cloud, and another part will be reflected to the sensor, and this is this part which is reflected that will constitute your spectral signature at a given time. And I insist on that, this is at a given time. In agriculture, in the agriculture domain, what is really important is to have this spectral information at regular time. Because a cropland is not a land cover. A cropland is a land use, and the land cover associated with your land, with this class, is an alternance between a bare soil, and then the vegetation is growing, you have vegetation, and then the harvest. And so this is the compilation between the spectral and the temporal dimension that you will have to interpret, to classify. So when you look at the spectrum, you can look at 3 different parts of the spectrum to examine the response. The first one is the one that we know better, the visible and the near infrared, middle infrared, then you have the thermic infrared, and then you can also have the hyper frequencies for the SAR. So typically, I will show you the typical spectral response for the bare soil, the water, and the green vegetation. These will be my reminders, and then we will move on. So for the bare soil, the radiation will be only influenced by the superficial layer of the soil. So typically, it will be influenced by the soil structure, the texture, the stony component, and also the soil organic matter and the soil moisture. So a typical profile of bare soil is that it will be low in the visible, and it will gradually and slightly increase until the near infrared, and then it becomes stable with the water, the absorption band of water here at these 3 measurements, which is typical for all the land surface elements. Then you have the water, where there is a very high reflection in the visible and almost no reflection in the near infrared. So when you display your image in the near infrared, the dark pixel will probably correspond to the water. And then you have the green vegetation, where here the radiation will be reflected, absorbed, transmitted, emitted by the plant. And what will be important for this phenomena, this is the pigments, the cell structure of the plant, and the water absorption. These 3 components will have an impact on the spectral signature that you will get. So for the water, I already mentioned the 3 classical absorption bands. And then moving to the pigments and the cell structure. So for the pigments, so in a green plant, this is almost the chlorophyll. So the chlorophyll will absorb a lot the visible radiation, especially the red, for the photosynthesis, and it will reflect, not use the near infrared because this is of no use. So you have here the link between the photosynthesis and the absorption. So high photosynthesis, high absorption of red, and almost no absorption of the near infrared, which is reflected. And the reflection of the near infrared will also be influenced by the cell structure of your plant. So depending on which kind of structure you will get, you will have different efficiencies in the reflection of the near infrared. So this is, I have presented you the spectral signatures looking at the individual bands, and for sure you can also just use vegetation indices. So just combine these spectral bands in a most efficient way to highlight the vegetation, the response of the vegetation, and to limit the response of the other factors, typically like the soil. In agriculture, you want to minimize the effect of the soil during the first stages of the growing cycle. There are a lot of vegetation indices, so the most common is the NDVI that you all know, but in fact you can create vegetation indices as you want. You need just to understand which band is important to what you want to detect, and then you can combine them in a way to optimize the answer of the phenomena you want to look at. I told you that there is a difference between the spectral response and also the spectral temporal response. So in agriculture, this temporal dimension is really important. And so here you get a typical, let's say, agricultural landscape in our country. So where you have winter crops and summer crops. They are here, and so you can see here that we are at the beginning of the season. So start of vegetation for the winter crops. So we have in false color, so the vegetation will appear in red. And so the vegetation is growing for the winter crop. Still no vegetation for the summer crop. The vegetation for the summer crop is arriving. There is the harvest for the winter crop, while the vegetation is at its full stage for the summer crop, and then it will be harvested. And so just taking the good period is already a good way to discriminate between the winter crop and the summer crops. This is the most easy discrimination in cropland: summer crops, winter crops. The temporal dimension is also well known. When you look at your NDVI profile, you all have done that, but this is typically the case. You have the increase of the vegetation and then the decrease. So for the SAR data, I will not spend much time on that because you have heard about the SAR during 2 hours this morning, and Ramon probably surely talked about it much better than I can do. But so the measurement will be influenced by the roughness and by the soil moisture, water content of the soil. And what is really important for agriculture, why do we use SAR, and why SAR can be very useful in complementing Sentinel-2? This is because of the density of the acquisition. This is the main reason in agriculture. So Sentinel-2, it's not because you get an acquisition that you get an observation. So there are clouds. It depends, of course, of the region of interest. But if we are talking in my country, for instance, the cloud is very, very difficult to manage. And so having this SAR data where you get information each time you get an acquisition will really allow to capture the different growing stage of your crop. So even if the signal can be a bit more noisy, that you don't have the 10 meters, it can be really useful. So the backscattering and the currents are two key, let's say, kinds of signals that can be useful for agriculture. So I guess you have been introduced to these two this morning. So the backscattering is the measure of the outgoing radar signal that the target redirects to the sensor, and the currents is a measure of the change between two sends every 6 days. And so if you have a high current, it means that there is no change. So your target is very steady. And if you have a change, the currents will decrease. These are examples of composites you can get, information you can get using the currents. So on the left, you have an RGB composite where in the red channel, we have the mean of the July currents, so monthly currents from July. In the green, the monthly currents from March, which is in fact the picture on the right. And on the red, this is the standard deviation of the currents over a season, a 6-month season. And so you can see that going to crop type is feasible only with the currents data. And when you look at the profile, if your pre-processing is well done, this is very pure, and this is very nice to interpret. Of course, this is Netherlands. Netherlands is probably the best place to demonstrate the SAR utility, usefulness, because this is very flat, and your fields are relatively regular, big, and I mean, this is not always like that in other countries. Okay, this was for the reminders, and now we can jump into the main topic of the talk today, so crop classification. And I will start with the crop definition, and then I will ask you maybe if you can try to define what is a crop. Your crop definition. You are all interested in agriculture. I guess you all have done or imagined that you could do a crop type map or a cropland map. How would you define what is a crop?
Defined by the national regulation.
Sure, okay. Okay, I take note. I will come back, but other definitions or other elements.
The plant grown in a specific pattern, that is crop.
Sorry?
Any plant that is grown in a specific pattern within a time, that is crop.
Mm-hmm.
Usually it's a homogeneous combination of one species. Can be more, but usually it's one species for a human purpose, for human use.
Please? Planted plants, yeah. Okay. Any other suggestion or element that has not been discussed? Okay. So, I will come back to the different elements that you have mentioned. Independently from remote sensing, this is the definition that you can find, a summary of the definition that you can find on internet. So a crop is any cultivated plant, fungus or alga, which is harvested, and whatever the use. Food, clothing, livestock fodder, medicine, biofuel, or whatever you want. But so the condition is cultivated plant, fungus, or alga, which is harvested, and stop. Then you can imagine that with this definition, your crop class could be really a mess. And so we need to refine it a little bit if we want to have a good map in the end. And for sure, there is a refinement to be done from the thematic point of view. And then there is a refinement to be done based on the tool that you will use. Because the definition is driven by the content, but shall also be driven by the tool that you will use. You cannot define something that you cannot measure with the tool that you use. These are the two elements that shall drive the definition. As I mentioned at the beginning, a cultivated land is not strictly speaking a land cover class, but rather a land use. Still, most of the land cover maps that I know have at least one or two crop classes included in their legend, and this is simply because the crop is so important that it cannot be absent from the legend. But a global map or even a regional or national map with one class, which is cropland, then if you really are interested in measuring the cropland, it can become very difficult to understand what is behind this class. And so, does it include the pasture? Does it include the temporary crops? Is there a difference between irrigation and not irrigation practices? And so, there are some limitations in using this, what I call general land cover map for crop application. Building a typology is something that is really, really challenging, and to help us, our colleagues from GTOS, so the Global Terrestrial Observation System, recommends us using the LCCS. I don't know how many out of you know the LCCS. Maybe you can raise your hands, those who know it. Okay, so the LCCS is not very popular, I would say, at least in this audience. So this is the land cover classification system. It has been introduced and defined by FAO at the beginning of the 2000, I think. And they propose a system to build the legend, which is organized in two phases. So the first one is something which is dichotomous. This is this graphic. So you need to define if your class has vegetation or not, is terrestrial or aquatic, is artificial or is natural here. And so by taking this decision, you have 8 building blocks. And then from these building blocks, you can optionally add information using classifiers. And these classifiers, so they are not mandatory, while this is mandatory. These classifiers allow you refining the definition by specifying what is the vegetation life form. Do I have tree, shrub, herbaceous cover? The leaf type, the density of the life form. If I have in a non-vegetated cover types, is it bare soil, is it built up, snow, ice, etc. And then you can use and combine these classifiers, and at the end you get a very complete definition of your class. What is nice with LCCS is the fact that if everybody would use it, at the end, all the classes of all the maps would have a definition made with the same tools. So this is not important that the crop class is the same in all the maps, but this is important that all the crop classes from all the crop maps are defined with the same tools. Because in that way, when you want to compare, you know exactly how to compare. The crop in my map A and the crop in my map B, they are not the same, but I know what I can compare and what is the overlap between the classes. Unfortunately, not everybody is using LCCS. Most of you do not use it. And why? This is because the classifiers are defined so precisely that it is very difficult to match these classifiers and the real world. So there is a gap which is too important between the reality of your area of interest and the classifiers. So for instance, the classifiers for the tree cover density, you need to decide if your tree cover is between 0 and 15%, 15 and 40%, 40 and 60%. This is simply impossible to do that. And so at the end, people who are using LCCS in the legend, so they have a very well defined legend, but what is within each class does not correspond to the legend. So there was something wrong on this. And so LCCS has recently evolved into the Lankover macro language, where they have changed a little bit the concept. They built some database where what they call classes or elements, so very basic elements, not a class, very basic elements of the landscape. They characterize it, still using the concept of classifiers. And this is what they call the map producer's domain. And the end user domain, meaning the people that will build the typology, will in fact combine these elements to create a class. And so you can create the class that you want, but the elements that will be used to create your class shall be in a way standardized. Using this macro language, that would be the model for the cropland. So it looks like very complex, and in fact it is, because this model wants to tackle the full diversity of the cropland all over the world. But it is not because this is complex that you need to use all the levels. So you can see that this is hierarchical, and so you don't need to go to the last level of detail to define what is your cropland. You can stop here. Maybe this is enough for you. Why do I have introduced you this macro language? First, I think this is important that you know that some standardization tools exist. And second, because this Lankover macro language has been used by the World Food Programme to define their to design their cropland definition. So the World Food Programme has defined in 2010, and this will be valid for the next years also. So they cropland by distinguishing between arable land, cropland, agricultural land, and land used for agriculture. So the arable land is used in most years for growing temporary crops during a 12-month period. So there is also a temporal reference in the definition of the crop. There is a subtlety. The arable land also includes the land that would normally be so used, but is lying fallow or has not been sown due to unforeseen circumstances. It does not include the land under permanent crops, or the land that is potentially cultivable but is not. Then you go to the cropland. The cropland is the arable land plus the land under permanent crops. The agricultural land, which is the cropland plus the permanent meadows and pasture. And the land used for agriculture, which is the total of agricultural land and the land under the farm buildings and the farmyards. I've shown you that because even if you decide not using this definition, which I could totally understand, I think this is important. You know that it exists because this definition will be used by international institutions to report about agriculture. And so they will issue statistics, they will compare countries, they will talk about the evolution of agriculture over time, and they will use this definition. And so when you will do your research and you will get some results that you want to compare with that, you need to know what they are talking about, how they define the arable land, and how they take into account the permanent crops, for instance. But this definition is a general definition, not really tuned to the remote sensing data. And so there is a proposition of GCAM to tune this definition to be compatible with the remote sensing data. So yesterday Pierre told you a little bit about GCAM. I don't know if you remember remember it. Sorry. So GCAM is a network of laboratories, researchers all over the world that have decided that are working on agriculture with remote sensing and that have decided to collaborate. So they collect in situ data on their places and they are doing experiments where they compare their results. And so the objective is to understand why a methodology is working well in this condition and why not so much in other conditions, and they publish. and they can also share the data, not during the current years, but years after. And they also propose some guidelines, or like this one. And here the annual cropland definition of GCAM is a piece of land of minimum 0.25 hectare, so minimum width of 30 meters, that is sowed, planted, and harvestable at least once within the 12 months after the sowing or planting date. And this is the definition. And so to come back to the different elements that you mentioned at the beginning, I think that the many elements were mentioned. So there is the concept of homogeneous species, where there we are already in the crop type definition, but this is true that if we go for the crop type, we have the species that comes. About the regulation, so the regulation can be a definition, but not from a remote sensing perspective. And so for the CAP, there is this CAP reform that is ongoing for the moment, where we need to use the Sentinel data to support the CAP reform. But a key question is to think about what is the regulation saying and what can I measure with Sentinel data. If this does not match, there is no change. I'm not saying that we need to change the regulation to fit the properties of Sentinel data, but you cannot oblige to detect something with Sentinel data if it's not monitorable.
Sophie, sorry, one question. So for instance, in this definition, I don't know, a method like alpha.
If I may, because I think.
Question on if, for instance, alpha meadow that stay on the same piece of land for 3 years and is always vegetated, is not within this category, if I'm not mistaken.
Exactly. But alpha, it depends also how you cultivate your alfalfa. If the alfalfa, like
usually
is
3 years.
Exactly. If it is harvested, this is included, because this is sown and harvested within a 12 months period. And then there is the succession of tree.
Yes.
But it means that you have tree cultivation during 1 year, but alfalfa would be a crop.
Okay.
It would fit the definition.
Thanks. Thank you.
Okay. Oops. Any other question on the crop definition before we go to the algorithm?
Just the WFP definition.
Yeah.
Just wanted to ask you about the alignment of the definition by WFP with the definitions of UN Statistical Division for the SIA, basically. If that is, there's alignment there.
I don't know.
Okay.
I could not. I know a little bit the definition, but not in the good level of the detail to answer your questions. Maybe you have a... You don't know. My opinion is that this is a pity that these institutions do not coordinate better on the crop definition. But this is a personal feeling. Okay. So, the last slide on the crop, just to show that there are also products that only focus on crop, not general land cover maps. So you have at global scale different cropland, non-cropland masks. The one from Modis, which is well known. There is also this unified cropland layer at 250 meters. So this product, in fact, is a combination of all existing products. Not only a single combination, but the selection, by pixel, they have looked how many products are saying that it is a cropland and what is the confidence. And so there are some rules to assemble the products in the end. And when you if you want to go to the crop type level, then you don't have any product at the global scale. So you need to go down. Usually this is national scale or even more local, at the local level.
Just wanted to mention that this year product was rolled out by USGS of Professor Tenkabel. So maybe, it's even with the better resolution than this one. You should check it out here.
Okay, thank you. Okay, classification. Mapping is the interpretation of your signal, so the radiance, in terms of land cover class. The problem is that there is no direct links, inference between the radiance and the land cover class, and so you have in between to do a series of processes to interpret this in terms of land cover classes. And these processes have evolved for sure. So at the beginning, the mapping system were just on-screen visualization of one or two images, and so the quality of the map depended on the expertise of the interpreter. Then we have moved because more and more processing tools have supported this interpretation, and we have also moved from the analysis of one best image to the full-time series. And now we are in a period where we are big data, so big data processing, digital processing tools. These processing tools are more and more used with the objective to reduce our labor to process the data, and this is absolutely needed. I would like to really emphasize the fact that you should look at the data, the input and the output. This is not because your algorithm is going from A to Z without any error message that you will get a good crop type map or a good cropland map. So a lot of energy for the moment is spent in optimizing the algorithm, optimizing the resources, and so on. And this is good, this is needed, but in terms of usefulness and quality of the end product, this is not enough. You need to look at the data, input and output data, and you need to validate it to understand how you can use this product. And so I think maybe I will repeat it several times today, but I think this is very important. There is a session tomorrow on the validation, and it will be linked. So this is a generic workflow for the land classification with remote sensing data. So typically you have your raw data, some pre-processing, the features extraction, the classification, optionally some post-processing, and then you have your land cover map. You can also decide to work by object and not by pixel, and in this case you need to segment your image. There are also some training data that can be used. So training data if you are in the case of supervised classification algorithm, or auxiliary data for unsupervised algorithm that can come from field or from existing land cover maps. There is the definition of the typology. We have just talked about it before. So for all of these steps, there are different choice, conceptual choice, algorithmic choice, but I will insist that I think that it is the quantity and the quality of your input data will drive more the quality of your output than the classification algorithm. So we will review the existing algorithm. Each algorithm has advantages and disadvantages, but it will be more constrained. You will be more constrained by your input data than by the algorithm performances. So let's start with the classification. So high diversity of classification algorithms split into two main types, so the unsupervised one and the supervised one. So unsupervised means that you do not have any a priori information about the spectral signatures of your classes. And so the algorithm will group the pixels together in clusters based on similarities, and you will have to label the clusters afterwards. And then you have the supervised algorithm, where you use the training data set to calibrate your algorithm a priori, and then you apply this algorithm to all the pixels of your images. For the supervised algorithm, more and more there are some preparatory steps on the training data set which are cleaned, and there can be some iterations between the cleaning of this data set. You run the algorithm, you look at the accuracy, and you improve the training data set, and you go on like this until the output meets your requirements. So I will present you two unsupervised algorithms. The first one is the K-means. So the k-means is an algorithm where you need to decide at the beginning how many classes you expect, and you arbitrarily locate some seeds at the beginning, and then you assign each pixels of the image to the seed which is the most similar. So you compute the mean in the spectral dimension, temporal dimension, and then you have the clusters. The mean of the clusters becomes the new seeds, and then the process is repeated. You reassign all the pixels to the new seeds until you repeat until in fact some convergence is met, and so your clusters are rather homogeneous. Another one is the ISO data, so iterative self-organizing data analysis, which is very similar than the k-means, except the fact that the number of clusters can vary during the algorithm. So you start with by default numbers, but during the process, the distance between the clusters are measured. If two clusters are too close, then they are merged. And the standard deviation of each cluster is also looked at. And if this standard deviation is too high, the cluster is split. And so at the end, this is the algorithm that will decide the number of clusters. But in all cases, you need to label the clusters. So this is really the easy thing. You have different clusters, and you need to define which cluster corresponds to each classes. But in reality, this is often much more complex. You need to work in many dimensions to be able to label correctly the clusters. So for the supervised algorithm, we have the maximum likelihood. This was probably until recently the most widely used method, and in this algorithm, the decision is based on probability. So each target class will be statistically described by what we call the multivariate probability density function. And there is an assumption that this function is follows a Gaussian distribution. And then each pixel will be compared to the different function. For instance, you have a pixel here. This is a simple example in only one dimension. But so you have this pixel here, and you can see that the probability that it belongs to the class B is higher than the probability that it belongs to the class A. And so it would be assigned to the class B with a certain probability that gives you some confidence index to the classification. And for sure, you can work in more than one dimension. You can add several spectral bands and temporal dimension, and then the distributions will become more complex. The main advantage of this algorithm is that there is a full control of you. You can control totally the algorithm. It is easy to understand why a pixel belongs to the class A or to the class B, and if you repeat the same algorithm in the same conditions, you are sure that you will get the same result, which is not the case with most of the other supervised classification. The disadvantage is that the assumption that the density function follows a Gaussian distribution is often not true, and so when this is not true, your result can be questioned. And in terms of processing, the disadvantage is that the same set of features shall be used for all the classes, and so you can lose efficiency in your processing because it can become quite expensive. A second kind of supervised algorithm is the artificial neural network. So here, the objective of this algorithm is to mimic the human brain, which is able to see and analyze a lot of information coming from different sources and making link between these data sets. And so the neural network is like what we call a connection of artificial neurons, and this will make the link between all this information. Here, this is a very simple example where you have your input, your output, which are the classes of interest, and there is only one, what they call hidden layer, but you can add several levels of layers. The advantage is that this is much more accurate when you have very large data set than the maximum likelihood. It also supports the fact that the distribution are not normal, do not follow a Gaussian distribution, so this is more robust. And you can incorporate a priori knowledge and some realistic constraint because you can give some input data that corresponds to your area of interest. The main disadvantage is that this is like a black box, and it will be a disadvantage that will come back several times. So here, this is very difficult to understand why a pixel is in one class or in another one. Not the pixel that you know before the classification that this is wheat or that this is barley, but the pixel where you hesitate. The algorithm will tell you this is wheat. Okay, you have to trust it because this is very difficult to understand the story. Another kind of algorithm is the support vector machine. So this support vector machine is very popular. I think that with random forest, there are the two main ones that are used for the moment, with some emerging, new emerging ones. So this is a non-parametric statistical learning technique for solving a quadratic optimization problem. So basically, what it means, so you are working in an input space in a given dimension, and the algorithm will not work with all your training data set, but only on the training data that are at the edges of the distribution. So the data that will help making the difference between the classes. It will localize these data in your space, dimensional space, and it will try to define the boundary. And this boundary then, based on the training data set, will be used to classify all the pixels of your images. If it is not able to draw a good boundary, let's say, then they will increase the dimensionality of the space by a kernel technique, and then they will work on what they call hyperplan, because the number of dimensions can increase a lot. And at the end, you always have a boundary that will discriminate between the land cover classes. So the advantage is that this is a method which is quite efficient when you have, let's say, small or incomplete, small training data sets. So if you do not have by crop type many samples, this method is robust because it will really look at the edges, and so it does not mind of the full population of your training data set. So usually when if you have a training data, if you have many training data for the read, for instance, you will have a distribution like this. And if you have few training data, if your data set has been collected correctly, you will have a lower density here, but you still should have this representativity in terms of in terms of variety of practices. So when you have few training samples, you lose the density, but we can expect that you still cover the variety of the practices. And so the SVM is efficient in this case because it is only working with this kind of points in the distribution. The disadvantage is that if you have noisy data, these noisy data are there, typically. And so it will have a dramatic impact on the classification performance because you think that this is representative or this will allow to make the difference between a wheat and a maize, and in fact this is a cloud, for instance. And so this is very sensitive to that. Another sensitivity is to the kernel function. I told you that when we are not able to define the boundaries in a certain dimensionality, we increase the dimensionality. The way we increase this dimensionality, if the kernel is not well used, there is a high risk of overfitting or oversmoothing, and so again, the performance of the algorithm will decrease. We move to another family, which is the decision trees. So here I think this is rather easy to understand. So this is quite hierarchical, and for each level you decide, you have a criteria or rule that is tested, and then you decide if you go in one decision, in one tree or in another one. So the advantages are very similar to the artificial neural networks. So handle a lot of the measurements. This is robust against the non-normal, non-frequency distribution. it is really easy to apply. You have few parameters, and the structure is transparent and easy to interpret. So this is not a black box in this case. But the disadvantage is that when you have feature space with high dimensionality, this kind of decision tree, single tree, is very difficult to handle that. And so more and more researches a few years ago have been done in this field of decision tree. And one of the, let's say, result of this research was the random forest. Random forest is also, like the SVM, one of the supervised classification that is mainly used. So this is an improved, what we can say this is an improved implementation of the decision tree, meaning that in fact it will test different decision tree and it will combine the results. So how does it work? So for each, they will in fact draw different trees with a random subset of your training data. And this is important to have it in mind. So you put your training data, and not all your training data will be used to build your random forest model. So there will be a random sample that will be used. The other one are not taken. They will do it several times with different random subsets, and then they will decide finally for your pixel the classes that is majoritary. So there is a majority vote between all the tests that have been done to decide the final label of your class. The advantage is that, for instance, you can cross-validate the results because not all the data have been used for training. You can use the data that have not been randomly selected to make a cross-validation, so you get quickly an idea of the quality of your algorithm, which is nice. You can also use this information to identify the discrimination power of the different features that you have used. Another advantage is that this is really easy to tune, so there are only 2 parameters. And the fact that it is more accurate than classical decision tree because you combine multiple classifications. The disadvantage is also the fact that it is combining a lot of classification made by random subsets. And so this random subset, this is random. Something which is also a disadvantage, and maybe I think for the cap, this is a big disadvantage. So sometimes there is the need to have something which is repeatable. You should run it several times, and you should get the same output at the end. With this random forest, this is not ensured because of these random samples that you do several times. And so for most of the pixels where the class discrimination is, let's say, rather straightforward, it will be the same if you repeat. But for the pixels that are the most difficult to map, you may have different results if you run different times. The last methodology I wanted to present is data mining, which is more and more used. So data mining is not an algorithm in itself. Data mining is more the process of looking in a wide variety of sources and making the link between these sources. And so here you will combine different algorithms, but you will also add a lot of other auxiliary information. And by the data mining, there will be linked between the pure classification and the other information. And so I think that this is more and more used. And it will come also in agriculture. It's already coming, in fact. So this is the summary. I will not read the slide because this is all what I have said, but you will get the presentation later on. So when you look at the literature, random forest and the SVM are probably the most widely used algorithm in crop mapping, crop type mapping, and data mining is coming. What is sure is that there is not a single best solution for all. I think that I cannot tell you that this algorithm shall be used for crop type or this algorithm shall be used for cropland. It really depends on the quality and the quantity of your training data. This is really important, and this will probably drive the choice of the methodology. Some words know about the other steps of the classification workflow. So If you decide to work by object, you need to segment your image, or you need to have polygons that are a priori defined. So in Europe, we have the chance to have, for each country, what they call the LPIS, so Land Parcel Identification System, where each field is delineated, and so you can use these polygons to force a by-object classification. If you don't have this polygon, you have to segment your image or your time series. So the segmentation is the division of your image into regions that we call objects, and these objects are made of adjacent pixels with similar properties. Properties can be spectral, spatial, or temporal properties. Then about the features extraction, I think that you have heard about it yesterday, and during the practical session yesterday, you already extracted some features. So basically, I would say that there are three categories of features: the radiometric, simple ones, so you use the spectral bands as they are, or some local textures. Temporal features, so you have to compute your profile and then derive some time descriptors. This is very important and interesting in agriculture. And object features, you can calculate some features like the mean of the reflectance, standard deviation of the reflectance, or shape features also that can be used in the classification. And then for the post-processing, it is optional. It really depends on which step you have defined before. So if you have done several classifications, you can just fuse them. Fusing the classification can be done by majority voting. You can also decide to take one classification for one class, or to work by object for specific classes and by pixel for the classes. Okay, again, this is your knowledge of the area that should drive this decision. You can also do like a simple filtering to remove the salt and pepper effect, like it is shown here. So these were for the, let's say, review of the algorithm. I will show you some results that we have obtained here. So this is an exercise where we have done cropland, not crop type, cropland classification in these countries, so Argentina, Belgium, Burkina, China, France, Madagascar, Morocco, Russia, South Africa, and Ukraine. So the objective to have all these test sites was to cover a diversity of agricultural practices. And we have done the cropland map using a random forest with field data, and using a random forest not with field data, but with training data extracted from a land cover map. I will show you later on how we did that. But just here, the result is very clear, that just to show the impact of the training data. So while here, for all the sites, maybe except Madagascar, where the fields are very, very small and the cloud cover is very high, but for most of the sites, you have an accuracy higher than 85%. While when you have the training data, which are less well defined, the accuracy can be much lower. So the quality of the training data is very important, and I will say a bit, but the performance is still acceptable in some cases, because the usefulness of the cropland maps is very high in countries, for instance, like where you have food security issues, or where you have some insecure situations. This is in this kind of country that this is important to know what will be the area which is cultivated this year, to anticipate if we will have enough, not enough, to anticipate the problem of the prices. And so in this country, typically, this is not possible to go on the field. So you need to find an alternative way to still get some information. And so here, this is a cropland map based on the CCI land cover map. So this is a global land cover map at 300-meter resolution with 2 classes of cropland. And we classified Sentinel-2 data at 10-meter resolution for the cropland, non-cropland. And you can see that the output is not bad. So surely it will not reach this level of overall accuracy or F-score, but this is not bad, and this is better to get this information than to get nothing. And so you should always balance the choice. So if you have the possibility to have your field data, this is perfect. When you don't have, there are still alternatives for the cropland, not for the crop type. And I think this is important to highlight, please. It works.
What's the size of your training data? Do you have the same size of your training data? Then it's unfair if you have different training size and then you use for the different country.
So what do you mean? The size of the
training
site?
data.
Or
Size.
The size of the site or the amount of training data?
I don't know how you choose a training that you use a point or use a polygon or you use, I don't know how you choose it.
So this is, I will go. So the size in Argentina, Belgium, and so on, this is one Sentinel-2 tile. This is the same size, the same extent, let's say, for all the test sites. And then for the test sites, we have worked with local partners that have shared their field data on the top, which have shared their field data. And then we have we have worked with the data that we have received. And so this is not the same quality of input data.
But so I think what she meant was, regardless of the quality of the training data, the size of the training data.
No, even the size, even the amount of samples is not the same between the size. So there are two kinds of samples, the cropland samples and the crop samples. The cropland samples were acquired not going on the field. They were acquired by digital interpretation of Google Earth because these are stable targets from year to year, let's say. This is more or less the same amount for all sites because it was done, there is no constraint on the cost of the field campaign. And then really the crop type information, if you are in Ukraine, for instance, so then the fields are very big and you have big roads, and so you go by car, and so in one day you can have hundreds of samples because they are by car, they take the GPS point and they look, and this is easy. When you are in Madagascar or in Burkina Faso, this is completely different. Then you will do a few samples within the day, and so you cannot imagine getting the same amount of data. This is sure that it affects the quality of the results, but that will be the reality. That will be the reality. You will never get a perfect training data set with the amount of data in a country like South Sudan, for instance, or it's just impossible. So I think this is true. It affects the quality, but it's realistic. And then for this second experiment, where we have extracted the crop information from the existing land cover map, then the process is homogeneous for all sites. This is the same. What is interesting here, and in the next slide also, is the fact that the overall accuracy of your cropland is reached rather quickly. You do not have to wait for the end of the season to have your overall accuracy high. So this is here in France, Morocco, Madagascar, and Sudan. And you have the F-score of your cropland, the non-cropland, and the overall accuracy. The first here is the mid-season, and then you add month. And so you can say that you get very quickly a good cropland mask. This is not necessarily the same for the crop type information. And there, for most of the crop type classes, you need to wait until the end of the season to have good accuracy for your mapping. Not all of them, there are some exceptions, and again, you need to know your area of interest. It mainly depends on the crop calendars. So here, in Morocco, typically, for the alpha-alpha, at the end of the season, the F-score is decreased, because at the end of this season, there is no more alpha-alpha. And so you better discriminate your alpha-alpha at the middle of the season. And so it may vary depending on the crop you want to detect, but usually mid-season, this is too early. You are just, all the crops have just emerged, and sometimes not all of them. Here, this is a comparison between the random forest and the support vector machine on the same sites. In general, the random forest classifier yields better results. And we have comparable results where, in fact, we have very few crop types in the legend. So then the discrimination was easier, and the supervector machine was able to perform as good as the random forest. Another example, we are in Belgium. We have done a per object crop type classification. And here we have used the dataset that I have introduced before, so the land parcel identification system. So this is a wonderful dataset. So in Belgium we have 460,000 parcels, and where for each parcel we know the main crop type that the farmer has declared. And so you can use this dataset to train the algorithm. In fact, we have only used 5% of this data set to calibrate the model, and the 95 remaining percent are used for validation. So you do not, this is important to mention. And we have mapped the 275 crop classes, so no a priori grouping in the classification. And in the end, this is the accuracy that you get, 88%, which is not bad with such a large amount of crop. Of course, I show you the overall accuracy, not the F-scores. So if I wanted to show you the F-scores of the different classes, all the minor crops would have a low F-scores, but they do not impact the overall accuracy.
Which images did you use?
Sentinel-2.
Only Sentinel-2?
Sentinel-2, the time series, I mean, not a, yes, the season, yes. March, no Sentinel-1 on this one.
Did you apply any negative buffer to the parcels?
For the training, yes. So for the training, we apply a negative buffer 5 meters, half of pixel. And we have the, for the training, I would say, and we have the conditions that only the parcels that have 3 Sentinel-2 pixels are classified. Minimum 3 Sentinel-2 pixels inside the parcel. Because we want to compute the mean, and so 3 is the really minimum to compute a mean and a standard deviation. So, but in Belgium, this is not a big constraint. If you go through other countries, this constraint of 3 pixels could be more difficult to handle.
And what was the average size of the parcel?
Yes, this is, I don't know. I mean, it really, because here we have included the grassland, so it changes the game. The grassland, this is much higher, much larger parcels. This, for the recording, you need to speak in the mic, even if you...
I'm interested, did you use some vegetation indices or only LPS classes?
I'm not sure I understand.
Vegetation indices,
yes.
Did you use?
Okay. So the features that have been used for the classifications are spectral bands and also NDVI and DWI. Okay. Both, both. Yeah.
Which algorithm?
Random forest.
By object classification and random forest, it means like first you did segmentation and then applied random forest over it, right?
This is not the segmentation because we already have the shapefile that defines the polygons. And so, in fact, what we do is by polygon, we compute the features, which are the mean and the standard deviation of the spectral bands and the NDVI and the DWI during the time, along the time series. So there is no segmentation, but we compute the features by object, and this is this by object feature that I used by the random forest.
Okay, thank you.
I will I will stop the questions because I still have one thing to present you, and I will need 10 minutes, and I need to stop at 30.
Just one question. How many iterations?
Sorry.
How many iterations did you
I think this was, I need to check. I will tell you after. And I do not have all the configuration just in mind. Just after, sorry, I need to move. One more thing, Sentinel-1, Sentinel-2, just to add one more comment about the feature selection. So we have done some tests for the Cent4Cap. Here, how to combine Sentinel-1, Sentinel-2. You can see the different scenarios that have been done. Sentinel-2 only, Sentinel-1 only, the time series, Sentinel-1, some temporal features. So you have much less features over the year, or different combination of Sentinel-1, Sentinel-2, and Sentinel-1, Sentinel-2, everything. And so you can see crop type map. You can evaluate the results in terms of overall accuracy and in terms of F-score, number of crop classes by F-score category. So the number of classes which have F-score between 0.85 and 1, etc., etc. So for Lithuania, if you only look at the results, the best is, of course, the combination of everything or the combination of time series. You get the same kind of conclusions in Netherlands. But in fact, when you look at the result, the S1 or Sentinel-2 time series only, they are a bit lower, but not so much. And so then you need to decide, is it really important that you go to 95 instead of 94 in terms of overall accuracy? But you will have to compute much more features. And then never forget that sometimes it is not useful to use everything. This is just the message I wanted to pass with these slides. In Castilla y León, the same test has been done, and here, this is interesting. So Sentinel-1 performs less. The performance of Sentinel-1 is significantly less good than Sentinel-2. And why? Because in Castilla y León, you do not have any cloud. And so every 5 days, you get your observation at 10 meters. Adding Sentinel-1 at 20 meters will bring noise. And so in this case, Sentinel-2 only is enough for sure. My last point. What is very specific to Cent2Agri? Because you will use Cent2Agri a bit in the afternoon, and you will hear about it during the week. So Cent2Agri is an open source system that has been developed to generate 4 kinds of products along the season. And here, today we will talk about the cropland and the crop type map. So the classifications are rather straightforward. This is a random forest. Forget for the moment the bottom part. But so you have your level 2 time series. You have your in situ available. Some feature extraction, you use the field data, there is a random forest, and you have the cropland or the crop type map. This is very classical. There is also for the cropland map an option if you do not have your field data, we can extract or build some field data from a reference map. So what are the specificities of Cent2Agri? Here, some gap filling and temporal resampling of the time series, of the level 2 time series before being classified. I will explain. Then some preparation in terms of field data. We have already talked a little bit about that. An option for running the cropland mask without field data set. And the fact that when we are working at national scale, we stratify the country. We are not working by tile, and we are not working at a full national scale. So, on the level 2 preparation, so when we have in situ data, the random forest will run using the NDVI values calculated for all the dates of the time series. And so, because we are working at national scale, we want to have the same dates for all the pixels of the area. Even if you are in an orbit or in the next one, we want to have the same dates. And so this is very important. And so, in fact, what we do is that we make a gap filling, but we make a temporal interpolation with a regular time step, which is 10 days. And so even if we have the true data, we do not have we do not use this true data. We use the interpolated values every 10 days. I think it can seem a bit crazy if you have the data not to use them, but when you are working at large scale, to have the spatial consistency, this is more important to have the same dates all over the countries, and to do that, this interpolation is needed. When we are working without field data, then we will use temporal matrix and not NDVI at all dates. And so to have a robust extraction of the temporal matrix, we have to get a profile which is as smooth as possible. And so here we have added a Whittaker filtering also to improve the smoothness of the profile. So these are the two steps I wanted to mention. For the in situ data preparation, so in terms of data collection, as I told you, so crop type information is acquired from field campaigns, and non-crop type is obtained by visual interpretation of very high spatial resolution imagery. Then there is a quality control. Do not underestimate this step. It takes time. So we have received from some colleagues data sets where the GPS coordinates, for instance, were completely off. And so it's important to check that the data that you receive. And then we split the polygon for training and testing. And here the splitting is done by polygon and not by pixel. So we cannot use pixels from the same polygon to train and to validate. This is to make the validation fully independent. And then we randomly select the number of pixel samples inside the polygon. So the training is by pixel for crop and the not crop classes. And here I would insist that on the fact that you should keep the diversity of your classes in your training dataset. So this is not because you are expecting a cropland map that you should have a training dataset made of two classes, crop and non-crop. You should keep all your non-crop classes and all your crop types to train your random forest for the cropland mask. Because if you group all the classes within one big sample, no crop, the spectral signature of your big sample will be a mess. It will be anything. It will be a combination of water, forest, building, whatever. And then each pixel will have some similarity with this big sample. So keep the diversity of the classes. You reduce after the classification, but within your training data, keep this variety. Also for the crop type. Keep the variety of crop type even if you want to map the cropland. And I think that I have just 5 minutes to explain how we build the data, the training data when we do not have the field data for the cropland. So the training data is selected from an existing reference map. So by default, we are using a global land cover map, but you can use the map that you want. If you have a local one, this is even better. And we cleaned, the dataset is cleaned using a trimming. I will show you. And then which feature we will use for this. So generally the land cover map do not provide crop type information. You only have cropland. And so your cropland class, in fact, will include exactly what I said before. There will be not one spectral signature. It will be a mess of spectral signature. And so in order to have the best features, you have to have the features as generic as possible. You cannot say, okay, I want this date, because I know what I expect a spectral signature. You don't know anything. And I will show you. So for the reference map preparation, so the reference is there. This is cropland, forest, urban water. First there is an erosion to remove all the border pixel. And then you take all the pixels which remain for the different classes and you trim it. So trimming is that you have the distribution here in different spectral channels. This is illustrated in 1 dimension. You will remove the outliers, and then you will recompute the distribution with the remaining data, and then you will go on until there is no more outliers with respect to a given threshold that you will put. Doing that, you will keep only what we expect to be the pure pixels for each classes. So these are the pixels that will be used to train your random forest. And what I wanted to say about the features, so you don't know anything about the crop types that are behind the cropland class of your reference map. And so here we will in fact derive the feature by the interpretation of the band. We know that a crop is a bare soil, and then a vegetation, and then again a bare soil. The bare soil is visible in the red. So maximum red is a bare soil. And so you will look within your profile when is the maximum red. You take the 3 maximum red, and you have the date of the maximum red. And at this date, which can be different from one pixel to another, you extract all your values. You do the same for the maximum slope, minimum slope, which is the growing of the vegetation and the harvest of the vegetation. You take the date, you extract the spectral values of these dates. And the same for the maximum and the minimum NDVI. And so you do not have put any a priori in terms of date. You have searched in your profile the key moments, and the dates can be different from one pixel to another. If you have one crop type, two different crop types in two neighboring parcels, you still have to find the maximum red, the maximum NDVI, and the slopes. This is the same. This is the same, let's say, events in your growing cycles. But the date will be different because the crop type will be different. But the fact that you work with dates, with events and not with dates, tackle this difficulty. And I think that the stratification. Last information. So I told you that we are working at national scale. This is the objective of Cent2Agri. We cannot ensure field data at national scale. This is simply very costly. So all the tiles will not be covered. So we need to find a way to train the model over larger areas. And so we will stratify the areas. So it will avoid requiring a complete set of in-situ data for each tile, and also it can allow coping with some gradients because you can define your different strata in a meaningful way. So this is the example in Mali. You can see in orange the number of Sentinel-2 tiles. This is simply impossible to have training data over all the tiles. And so what we have defined with our Malian partners is that we have defined 5 regions. And within these 5 regions, we will use a single training data set that will be computed for all the tiles within, and that will be representative of the region. And this is the same here in Ukraine, where we have done a stratification based on soil map and agroclimatic map, or even in a more local area in Morocco, where we have split between 2 watersheds. So this is also important to deal with the difficulty of getting in-situ data. And also, if you have very contrasted region in your country, in terms of soil, in terms of relief, in terms of agricultural practices, it makes sense to not put everything in the same algorithm. And this is the summary. I let you read. Yeah, no, I will stop here. I let you read. I think that I have talked too much. Okay, thank you. I don't know if there are questions. We can have some questions here. Few minutes, and then I let you go to lunch. And I will stay here.
Thank you. Do you have some data that show how the classification result is improved when using these time-independent features as opposed to the raw time series?
Well, this is I mean, we have done this test by applying the time features only where we did not have the field data. So for the moment, we still have not decoupled both aspects. So the temporal features have been used when we do not have the field data, and so the difficulty is higher. So the next step we need to do is to apply these features also when we have the field data, and so the comparison can be done. What we expect is that the robustness will be higher with this, but the result will come.
If I heard well, you mentioned that you use 3 values for the maximum red, right? And then you add a date.
Yes.
So how do you decide for the date?
Well, the 3 values cannot be at different moment during the phenological. You take the date which is in between.
Okay. Okay.
So it just means that you have your 3 values. So the red basically will be in this kind. If you will have 1, 2, and you could have this one if this is this would be maximum, but the maximum will be here if there is a
Sure.
So this one will not be taken. We will take this one if there is a gap which is too high, and so we will locate the date here.
So you take the average of those 3 values.
If there is the average, and we look also at the deviation between the 3 measurements to avoid the fact that we can take the date here if we would take this one.
All right. Thank you.
Okay, I will let you go for lunch, but before I have 2 messages which are not about classification. So for the posters, most of them are displayed for the moment. Tomorrow, the poster session will be this afternoon at 5. Tomorrow before lunch, you must take your poster off because the panels will disappear during lunch. So do not forget to remove them before lunch tomorrow. And the last message. If someone has forgotten his glasses yesterday night, so there is a pair of glasses at the museum, at the secretariat of the museum. They found, I don't know if this belongs to this group, but if this is the case, this is at the secretariat of the museum and you can go, they are waiting for you. Okay, have a good lunch.